For over a century, the global energy system has been defined by separation: coal in one place, gas in another, hydro elsewhere, each source, isolated, built for stability in its own domain. But as the world races toward decarbonization, that era of isolation is ending, a new one is emerging, one defined not by a single technology but by connection. This is the story of the hybrid grid, where solar, wind, hydro, and battery systems merge into one seamless, intelligent network. Powers our planet day and night. For decades, renewables faced a single relentless criticism: intermittency. What happens when the sun sets, when the wind stops? The answer, once thought impossible, is now being engineered at a global scale. Across continents, hybrid renewable projects are proving that a clean grid can also be a stable grid. To see the future of energy, we must look to the pioneers building it today. Our journey begins in the vast, sun-drenched deserts of India. Here, solar panels stretch beyond the horizon, shimmering in the heat, paired with colossal wind farms that stand ready to harness the monsoon's formidable strength. This is the Khavda Renewable Energy Park in Gujarat, a project of staggering ambition, set to become the largest power plant of any kind in the world, with a planned capacity of 30 gigawatts. These are not just separate solar and wind projects sharing a fence. They are deeply integrated hybrid systems. By co-locating generation sources, developers can share critical infrastructure like transmission lines and substations, drastically reducing costs and land usage. The result is one of the world's first and largest integrated hybrid parks, a landscape where the wind, often strongest at night and during the monsoon season, complements the sun's reliable daytime power. But the true innovation lies in the third element, energy storage. As night falls, the wind continues to generate power, charging massive grid-scale batteries. When the sun rises, these batteries discharge to help meet the morning peak demand before the solar panels take over to power the nation's industry. This synergy creates a smoother, more reliable power profile, turning the intermittent nature of renewables into a predictable, dispatchable asset. It's a model of efficiency designed to deliver clean power 24/7. Thousands of kilometers away on the edge of the Sahara, a different experiment unfolds. In Morocco, the Nouazati solar complex isn't just capturing sunlight, it's capturing heat itself. This remarkable facility is a blend of two solar technologies. Standard photovoltaic arrays, familiar across the world, sit alongside a marvel of engineering, concentrated solar power, or CSP. Here, a field of over 500,000 mirrors called heliostats track the sun with precision, focusing its rays onto a central tower. This concentrated energy heats molten salt to over 560 degrees Celsius. This superheated salt acts as a thermal battery, storing immense heat that can be used to create steam and drive a turbine, generating electricity long after sunset for up to 7 hours. It's the perfect balance between light and time, providing Morocco with energy independence and the potential to export clean power to Europe. In China's Gansu province, the challenge is one of sheer scale. This remote windswept region is home to one of the world's largest onshore wind projects, but its immense generating potential is located over 1,000 kilometers from the country's bustling eastern cities. The solution is a renewable energy base where vast corridors of wind turbines share ultra-high voltage transmission lines with equally massive solar installations. By combining the complementary generation profiles of wind and solar, China ensures that these hugely expensive transmission corridors are utilised as efficiently as possible, minimising the costly problem of curtailment where power is wasted because the grid cannot absorb it. It's a monumental feat of infrastructure, a testament to long-term planning on a national scale. Further south in Australia, the challenge isn't just generation, but stability. The country's long, stringy grid is vulnerable to fluctuations. Here, large-scale battery storage facilities like the pioneering Hornsdale Power Reserve are the grid's shock absorbers. They don't just store energy for later use, they provide critical grid services. When a fault occurs, these batteries can respond in milliseconds, faster than any conventional power plant, injecting or absorbing power to maintain grid frequency at a stable 50 Hz. This rapid response prevents cascading failures and blackouts, providing the essential stability needed to integrate ever higher levels of fluctuating renewable power. In Chile's Atacama Desert, the driest place on Earth, we find one of the planet's most intense solar resources. Projects here are leveraging this incredible solar potential by pairing it directly with advanced battery storage. During the day, the solar farms generate vast amounts of low-cost electricity, powering the country and charging the batteries. As the sun sets over the Andes, these storage systems seamlessly take over, dispatching clean energy throughout the evening and night. This solar plus storage model is so effective that it's outcompeting fossil fuel plants on cost, fundamentally reshaping the country's energy market and providing a blueprint for sun-rich regions worldwide. Across the American Southwest, a new generation of energy hubs is emerging. Projects like the Edwards and Sanborn facility in California combine solar, wind, and a massive battery array on a single site. This tri-hybrid model creates a powerful, resilient energy source. Solar dominates the sunny days, wind captures energy during stormy weather and at night, and the battery smooths out the gaps, ensuring a constant flow of power. These hubs are designed to meet the ambitious 24/7 carbon-free energy goals of corporations and cities, acting as self-contained ecosystems of clean power, and in Europe, particularly in the mountainous terrain of Scandinavia and the Alps, the grid leverages nature's own battery hydroelectricity. For decades, vast reservoirs have provided dispatchable power. Today, they play a new crucial role in the hybrid grid. When solar and wind generation is abundant and cheap, pumped hydro stations use that excess electricity to pump water uphill to a higher reservoir. Later, when clouds cover the sky or the wind dies down, this water is released, flowing back down through turbines to generate power. It's a simple, elegant, and large-scale storage solution, turning entire mountain ranges into giant rechargeable batteries for the continent. From India to Chile, from Australia to Morocco, these projects are more than just power plants. They are living laboratories, each one a unique composition of technology and geography. Together, they form a global orchestra of energy, with each instrument tuned to the rhythm of the planet, playing the symphony of a sustainable future. But hybridization isn't only about hardware, it's about intelligence. Artificial intelligence and predictive analytics are becoming the invisible backbone of the modern grid. Algorithms forecast demand, anticipate weather, and balance energy flows across thousands of kilometers. It's not just renewables, it's responsive. The heart of this revolution is storage. From lithium-ion megabatteries to new materials like sodium, flow, and solid-state cells, storage technology transforms renewables from intermittent to continuous. Every innovation brings us closer to the elusive dream of 24/7 clean power. Yet behind the incredible technology of hybrid power lies the undeniable force of economics. For any large-scale transformation to take hold, it must make financial sense. The story of the global energy transition is at its core a story of shifting economic tides, where the numbers on a spreadsheet are becoming as powerful as the electrons flowing through the wires. It's a transition driven not just by policy or ideals, but by the fundamental laws of the market. For decades, the global energy system was built on a simple economic premise. Fossil fuels thrived not because they were inherently better for the planet, but because for a long time they were cheaper. The entire infrastructure of our modern world, from massive centralized power plants to the global shipping lanes that carry coal, oil and gas, was optimized around the low cost of extracting and burning carbon. This economic advantage was so profound that it became the default, the unquestioned foundation of industrial growth and prosperity. The environmental costs were treated as externalities, footnotes in the grand economic equation. That equation is now fundamentally and irreversibly changing. Over the past decade, a quiet revolution has been taking place, driven by massive economies of scale, technological innovation, and sophisticated manufacturing. The cost of renewable energy has plummeted. The levelized cost of energy, or LCOE, a measure of the total lifetime cost of building and operating a power plant divided by its total energy output, tells the story. Solar, photovoltaics, and onshore wind have seen their costs fall by nearly 90% and 70% respectively. When paired with increasingly affordable battery storage, hybrid renewables are now the lowest cost form of new electricity generation in history. This isn't a future projection, it's the reality in markets around the world today. For utilities and developers looking to build new power capacity, the economic choice is clearer than ever. The argument is no longer about subsidizing green energy, it's about choosing the most affordable, reliable, and future-proof investment for the grid. We see this playing out globally. In countries like India and Chile, competitive auctions for new power capacity are consistently won by clean energy bids that dramatically undercut existing coal and gas plants. These aren't just marginal victories, they are decisive economic statements signaling that the era of fossil fuel dominance is ending market by market. In the United States, hybrid projects are reshaping regional energy markets from the ground up. In areas with abundant sun and wind, like the desert Southwest and the Great Plains, developers are building massive hybrid hubs. These projects combine gigawatts of solar and wind generation with large-scale battery storage capable of delivering firm, dispatchable clean power around the clock. They are transforming intermittent resources into reliable base load-like assets that can compete directly with traditional power plants on both price and performance. Because of this undeniable economic shift, the energy transition is no longer primarily ideological, it's financial. Investors, asset managers, and corporate boards are now analysing energy decisions through the lens of risk, return, and long-term value. The volatility of fossil fuel prices, coupled with increasing climate-related financial risks, makes clean, price-stable hybrid energy an incredibly attractive proposition. It represents a move from commodity risk to capital investment, a fundamental change in how corporations manage their energy exposure. But this transition isn't uniform. The economic drivers and models for hybrid energy look very different depending on where you are in the world. While developed nations focus on decarbonising and modernising vast existing grids, many parts of the developing world are facing a more fundamental challenge: energy access. For hundreds of millions of people, the centralised grid model has failed. Extending massive transmission lines over vast, difficult terrain to serve low-density populations is often economically unfeasible. Here, hybrid microgrids are not just an alternative. They are a revolutionary leapfrog technology, bringing reliable electricity to communities for the first time. A single self-contained installation, a field of solar panels to capture the midday sun, a small wind turbine to harness evening breezes, and a local battery to store the energy for use overnight can power an entire village. It operates independently, no need for a central grid. It produces no local air pollution and no carbon emissions. It delivers more than just electrons. It delivers light, independence, economic opportunity, and a connection to the modern world. In land-scarce regions like Southeast Asia, another innovative hybrid model is taking hold by deploying vast arrays of floating solar panels on the reservoirs of existing hydroelectric dams. Countries are creating powerful synergies. The solar panels generate power during the day, reducing water evaporation, while the hydro plant can store water and dispatch power at night or during cloudy periods. It's a brilliant way to use existing infrastructure as a dual-purpose asset, saving precious land while doubling the clean energy output from a single site. Meanwhile, in the corporate world, some of the planet's largest companies are quietly rewriting their own energy codes, moving from passive consumers to active drivers of the clean energy transition. For tech giants with massive power-hungry data centers, energy is a critical operational cost and a key part of their public identity. Companies like Google, Apple, and Microsoft are pioneering a new gold standard: true 24/7 carbon-free energy. This goes far beyond simply buying renewable energy credits to offset annual consumption. The goal is to match every kilowatt hour of electricity consumed with carbon-free electricity produced on the same grid every hour of every day. Achieving this requires a sophisticated portfolio approach, building hybrid power purchase agreements that blend solar for the daytime, wind for the night, and storage to fill the gaps, ensuring their operations are powered by clean energy around the clock. But this new economic and operational landscape, driven by hybrid systems, also comes with immense challenges. The simplicity of the old system is being replaced by a new era of complexity. Grid operators, accustomed to a few large dispatchable power plants, must now manage thousands of distributed variable energy sources. Transmission congestion is a major bottleneck, as the best renewable resources are often located far from population centres, requiring massive investment in new power lines, and the regulatory frameworks and market rules designed for a bygone era often struggle to keep pace, creating barriers to entry and slowing down the interconnection of new clean projects. Furthermore, ensuring a just transition is critical, supporting the workers and communities historically dependent on the fossil fuel economy as the market shifts beneath them. Building the hybrid grid of the future isn't simply about stacking more renewables onto the system. It's about creating a new dynamic and intelligent energy ecosystem. It's about orchestrating a complex symphony of solar, wind, storage, and demand, all coordinated in real time to deliver clean, affordable and reliable power for everyone. The economic case is made. Now the work of integration begins. As we weave together the world's renewable resources, this orchestration is becoming one of humanity's greatest engineering achievements, a digital nervous system for the planet. It's a living network, pulsing not with data, but with the very energy that powers our civilization. For centuries, the global map of power was drawn by the geography of fossil fuels, creating dependencies and conflicts. Now we are witnessing a fundamental rewiring of that map. In the future, nations won't compete over oil pipelines, but over clean power links. The arteries of this new global grid are the superhighways of electricity, high voltage direct current or HVDC cables. Unlike traditional alternating current, HVDC can transmit immense amounts of power over thousands of kilometers with minimal loss, making it the key technology for connecting continents. These are not just cables, they are the new conduits of influence, trade, and energy security. Ambitious projects are already underway, laying the groundwork for this interconnected future. The Australia-Asia Powerlink, for example, aims to build the world's longest undersea HVDC system, stretching over 4,200 kilometres. It's designed to export solar power from one of the sunniest places on Earth in the Australian outback to power over 15% of Singapore's needs. Similarly, the proposed India, Middle East, Europe economic corridor isn't just about goods and data. It includes a strategic energy cable to share green hydrogen and renewable near-normal electricity, binding 3 regions into a new energy partnership. For the first time in history, electricity itself becomes a truly fungible, globally traded resource, clean, infinite, and shared. This creates a new paradigm. Nations rich in sun, wind, or geothermal potential can become the energy powerhouses of the 21st century, exporting their abundant, clean power to neighbours and allies. This isn't just about selling kilowatt hours, it's about creating a more resilient and diversified global energy market, less susceptible to the price shocks and supply disruptions of a single fuel source. This profound shift will reshape geopolitics as much as it reshapes energy. The logic of energy security is being inverted. In the 20th century, security meant controlling finite resources. In the 21st, it means fostering interconnection and mutual reliance. This requires a new level of international cooperation, not just in engineering, but in regulation and policy. Nations must work together to harmonize grid codes, establish fair cross-border tariffs, and create transparent market rules. The challenge is immense, but the prize is a more stable, peaceful, and prosperous world. The possibilities are staggering. A sunlit desert in Australia could power homes and businesses in Singapore. The immense untapped hydropower potential of the Congo River in Africa could one day help stabilize Europe's grid, providing clean, firm power to balance intermittent wind and solar. The wind-swept plains of Patagonia could export energy to industrial centers thousands of kilometers away. This is the power of a globally integrated hybrid system. It smooths out the natural variability of renewables by connecting different weather systems and time zones. The map of power is being redrawn, but this new map comes with its own set of challenges. The transition creates new dependencies not on fuel, but on technology and critical minerals. The supply chains for lithium, cobalt, copper, and rare earth elements essential for batteries, wind turbines, and transmission lines are highly concentrated. Ensuring these supply chains are secure, ethical, and sustainable is a paramount geopolitical task. We must move from a linear take, make, dispose model to a circular one, investing heavily in recycling and material science to reduce our reliance on primary extraction. Furthermore, this transformation will have a profound impact on the workforce. While jobs in the fossil fuel industry will decline, a massive new workforce is needed to build, operate, and maintain this new energy infrastructure. We need grid operators, data scientists, power electronics engineers, battery technicians, and policy experts. Ensuring a just transition means investing in retraining and education, creating pathways for workers from old industries to new, and ensuring the benefits of this clean energy revolution are shared by all. And as this monumental transformation unfolds, one truth emerges with startling clarity. Hybrid energy is not just a technical solution, it's a philosophical one. It represents a fundamental shift in our relationship with energy, with nature, and with each other. It reminds us that true, lasting resilience is born from diversity, and that enduring balance comes from integration. For too long, we sought to dominate nature, to extract and consume. Now we are learning to partner with it. From the smallest off-grid village finally gaining access to reliable power, to the largest continental supergrid managing the flow of terawatts, humanity is learning to work with the planet's natural rhythms instead of fighting against them. We are designing a system that thrives on the very variability we once saw as a weakness. The hybrid grid, therefore, represents more than just technology. It is a powerful, tangible symbol of cooperation between nations, sharing their resources, between science and nature working in concert, and between the needs of today and our responsibility for tomorrow. The power that will define the next century is not new or renewable. It is adaptable, intelligent, and most importantly, shared. It is a power that connects us rather than divides us, a power that builds bridges, both literally and figuratively. This is the dawn of the hybrid energy age, an era defined not by scarcity and conflict, but by abundance and collaboration, an era where human innovation meets planetary harmony, and the grid that powers our world never has to sleep again.